Welcome to This Explainer. Today, we're diving into something I absolutely love calling the anatomy of everything, the foundational principles of chemistry. And look, chemistry isn't just some distant, sterile lab science. It's literally the fundamental operating system of the physical world. It decodes how every single piece of our universe interacts, shifts, and changes.
Dmitri Mendeleev really hit the nail on the head when he said, chemistry is the science of elements and their transformations. At its core, chemistry strips away all the crazy complexity of the world right down to its basic building blocks. It focuses entirely on how those blocks morph into brand new substances. Ultimately, it is the science of change.
So here's our roadmap for This Explainer. First, an introduction to chemistry. Second, what is matter? Third, the classification of matter. Fourth, the separation of mixtures. And finally, the law of conservation of mass.
Section 1. Introduction to Chemistry.
You know, a massive portion of the changes happening in the environment around us are actually chemical changes. And to really wrap your head around the scale of this, just think about the number 4 million. That's roughly the number of known inorganic compounds today. 4 million. It just goes to show you how unimaginably vast the study of chemistry really is. To actually handle all of this, we have to split the science up. We've got inorganic chemistry, which studies the elements in their compounds, how we make them, and how they're used in everyday life. Then there's organic chemistry, which specifically zeroes in on the compounds of carbon. And finally, analytical chemistry, which gives us the tools to figure out exactly what components are hiding inside a mixture and in what exact quantities.
Section 2. What is matter? So if chemistry is all about studying matter and how it changes, we kind of need a rock-solid definition of what matter actually is, right? Basically, matter is anything that has mass, occupies a specific space, and possesses energy. I really want you to absorb that triad: mass, space, and energy. Literally everything you can touch, breathe, or interact with is just a specific combination of these three things. And that relationship between mass and energy, it is deeply, deeply interconnected. To really grasp that connection, we have to talk about an incredibly large number: 3 times 10 to the 8th power meters per second. That is the speed of light in a vacuum, and it sits right at the heart of Albert Einstein's famous mass-energy equivalence equation, EMC squared. What this equation brilliantly proves is that mass and energy are perfectly interchangeable. For every specific quantity of energy, there's a corresponding mass, and vice versa. If a system releases energy, what chemists call an exothermic reaction, it actually loses a tiny, tiny bit of its mass. If it absorbs energy, an endothermic reaction, its mass slightly increases. It's just a phenomenal concept that shows how totally dynamic matter really is. But how do we actually describe all this matter? Well, we categorize its characteristics into 2 buckets: physical properties and chemical properties. Physical properties, things like smell, color, hardness, or electrical conductivity, describe matter without changing its core identity. You can measure them without breaking the substance down. Chemical properties, on the other hand, are all about the transformation of the composition itself. For instance, when you burn ethanol, it doesn't just stay ethanol. It physically transforms into carbon dioxide and water. Those new molecules are completely different from the starting ones, and that is a chemical property in action.
Section 3. Classification of matter.
So how do we systematically organize all this stuff in the universe? Well, it all starts with the number 118. Despite the near infinite mind-boggling complexity of our universe, there are only 118 known chemical elements. That's it. These are the fundamental building blocks of everything. When we talk about an element, we're talking about a pure chemical substance that absolutely cannot be broken down into simpler substances by any chemical reaction. It's made of just one single kind of atom.
And there's this really strict dividing line in chemistry between those pure, unbreakable elements and the compounds that they form. While an element is just one kind of atom, a chemical compound is built from atoms of 2 or more different elements that are chemically bonded together in very strict fixed ratios. Take water for sure. It is always 2 hydrogen atoms bonded to 1 oxygen atom, H2O. And unlike elements, you actually can use chemical reactions to break a compound back down into its simpler elemental components.
But things get even more interesting and a little messy when we talk about mixtures. Because unlike compounds, which have those strict permanent ratios, mixtures blend substances in completely arbitrary, flexible ratios. And we classify them in 2 ways: homogeneous and heterogeneous. Homogeneous mixtures have the exact same composition throughout. You can't see the boundaries between the components.
Think of salt completely dissolved in a glass of water, or a hot cup of tea with sugar. Heterogeneous mixtures, however, are visibly divided. The substances keep their own identity, and you can actually see the boundaries. Ice cubes floating in water, sand swirling around in a glass, or even everyday things like smoke, milk, and fog. The individual components hold on to their original characteristics.
Section 4. Separation of mixtures.
Now, because the components in a mixture haven't actually chemically bonded to create something brand new, we can usually pull them apart using pure physical separation methods. We have filtration, which separates things based on particle size using a filter. Crystallization separates components based on their different solubilities. Distillation is brilliant for liquids. It separates them based on differences in their boiling points. Then there's extraction, which uses two unmixable liquids to draw out a specific compound based on how it dissolves. And finally, chromatography, which separates components based on how differently they move between a mobile phase, like a solvent, and a stationary phase. The huge takeaway here? Every single one of these relies purely on physical differences. The actual chemical identity of the substances is never altered.
However, sometimes those physical methods just aren't enough, and we have to bring in chemical separation. This is an incredible analytical technique where we purposefully trigger a chemical reaction to force a separation to happen. A perfect example is precipitation. You take a perfectly homogeneous liquid mixture, introduce a new substance, and it reacts to form a solid compound, a precipitate. Once that solid is formed right there out of the liquid, you can just use physical filtration to pull it right out.
Section 5. Law of conservation of mass.
Okay, so we've talked about what matter is, how it mixes, and how it transforms. But there is an absolute, unbreakable rule governing all of this. What actually happens when matter changes? Like when wood burns to ash and smoke, or when compounds are separated. Where does the stuff go? Is it destroyed? Is new stuff created out of thin air?
The answer was famously confirmed by the brilliant chemist Antoine Lavoisier, who carefully heated mercury second oxide and meticulously measured the results. He gave us the law of conservation of mass, which states, during a chemical reaction, the total mass remains constant. This tells us that the universe is highly orderly. Matter is never truly created or destroyed in these reactions, it only changes its form. It's quite literally the law of the industriability of matter.
Let's just walk through some really simple, elegant math to visually prove Lavoisier's point. If you take exactly 2 grams of hydrogen gas and react it completely with 16 grams of oxygen gas, you don't get 17 grams. And you don't get 19 grams. You get exactly 18 grams of water. Exactly what you put into a closed chemical reaction system is exactly what you get out. The sums are totally identical. Now, while Einstein showed us the tiny, basically immeasurable amounts of mass shift into energy, in classic chemical reactions, the mass is functionally perfectly preserved.
We've journeyed all the way from Mendeleev's simple definitions to the immense complexity of 4 million compounds, right down to Lavoisier's unbreakable law. So I want to leave you with this provocative thought. If nothing in the universe is ever truly lost, if every single atom of every compound is simply being rearranged and transformed over and over again, how does this unbreakable law of chemistry shape the way you view the changing world around you? Seriously, the next time you see ice melting, a fire burning, or even just sugar dissolving in your morning tea, remember, you are watching the brilliant, orderly anatomy of the universe at work. Keep exploring and keep questioning the wonderful transformations happening right in front of your eyes.